this first afternoon session of Wednesday. I'm Jerry McKenzie from Montreal. Our first speaker is Dean, whose co-author is Roy Tell, and his title is De-randomizing with Minimal Memory Footprint.
Thanks, Pierre. Do you hear me? Yeah, okay, good. So this is we've seen a lot of de-randomization up until now, so I don't need to convince you that we want algorithms that use fewer coins, same way that we want faster algorithms and those that use fewer space, right? Well, randomness is sometimes essential, but even when it's not, it's very useful also in the sense that designing efficient randomized algorithm is easier. And they also outperform deterministic ones in the sense that either we don't have efficient deterministic ones, but even when we do have, randomized ones often offer speed up over the best known deterministic ones. So let's see. We've just heard about polynomial identity testing in the morning session. This is an example where we don't know any efficient deterministic algorithm. But we can take, for example, primality testing. We do have both randomized polytime and deterministic polytime, but the randomized one is much more efficient and simple, right? And also in the space-bounded setting, we have connectivity in directed polymixing graphs. There is a very simple randomized log n space to solve it, whereas the best deterministic one takes log n to the 3/2. This is what Salil was talking about. Okay, so we have this gap, and obviously you all know the BPP versus P problem, and now you, after the last talk, you also know about the BPL versus L problem. Note that these de-randomizations, so the BPP versus P, we consider a polynomial factor blow up in time, whereas in the BPL versus L problem, we want a constant factor blow up in memory. But actually, we want to do better and have like a generic recipe for de-randomization, right? Either in terms of PRGs as a black box recipe that works kind of for any input and any algorithm, doesn't need to look on the input. But also we've heard about targeted PRGs, right, where we can replace true randomness that is only guaranteed to work for that specific input. Okay, on Monday, we actually heard quite a lot of, on that. And before moving to the space-bounded regime, let's talk like 2 minutes about the time-bounded setting and see what we wanted to do there. So we know that time-bounded de-randomization usually follows from the hardness versus randomness paradigm, where we trade hardness to pseudo-randomness, right? We treat the hardness of a function as a resource rather than an obstacle. And indeed, under complexity theoretic assumptions, we know that BPP is equal to P. So let's go over again the classical result by Impagliazzo, Nitsan, and Wigderson from the 90s. So let's kind of state it. We assume that we have a function f in E. So this is like the easiness part of the assumption, but that requires circuits of exponential size, like 2 to the 0.1n. Then we can take any randomized algorithm that runs in time t on inputs of length n and simulate it deterministically in time poly tn. This is great, but this poly is a large poly in classical works. And also in other more recent proofs, this poly is a large poly. And we want to do better, right? We want like a recipe that rates randomized algorithm to deterministic ones, but doesn't blow up the running time. And this is a recent line of inquiry where we ask, can we de-randomize with small time overhead? Good. So I don't want you to go over all this table just for the experts among you, if you're interested. I just want you to notice two things. First thing is, regarding to worst case de-randomization, the best we can, we know how to do kind of the optimal thing and to trade time t to time t squared, or t times n. This is kind of the first thing I want you to note. And second thing, the classical de-randomization assumes hardness for deterministic circuits. This is kind of a standard hardness assumption. But all of the super fast results kind of need to assume another thing, either a cryptographic assumption or some hardness assumption against non-deterministic circuits. Okay, so these are the kind of two takeaways I want you to get from this table. But this is for the fast time-bounded regime. And today, we're going to talk about the parallel in the space-bounded setting. Okay. So just a brief mention of the model. So we consider the standard probabilistic space-bounded computation model in which we have an input tape, which we're not allowed to touch, the random coins tape, which are initialized with independent and uniform random coins, the work tape or work tapes. And this is the only place we're allowed to do intermediate computations. For example, if you want to remember the coins we have tossed, we need to store them in our work tape. Okay, and if we want to output a value rather than accepting or rejecting, we can also have an output tape. And BPL, like Salil told us, is the complexity class of languages which are accepted by a probabilistic space-bounded machine with space complexity O log n. And our goal is to get rid of the randomness, of course, namely to take a space S randomized algorithm and to trade it into a space S prime deterministic one, hopefully with S prime being as close to S as possible. Okay, this is the BPL versus L problem. Now, unlike the time-bounded setting, we do have many, like we just saw, many explicit results. So I'm not going to go over it because Salil did a great job for me. So the last talk essentially covered almost all of these results. And I want to stress that these results are unconditional. Okay, they do not rely on any hardness assumptions. Okay. Good. But the point I want to make is that even when we prove BPL equals L, hopefully soonish, it's very likely that the question of what we called minimal footprint would remain. Namely, what is the minimal C for which this inclusion holds, for which BP space S is contained in D space C times S. So maybe, unconditionally, any C would be fantastic. But maybe conditionally, we can ask whether we can make this C very small, kind of to decrease the overhead that de-randomization produces. Right? Okay. Now, if we do allow ourselves to make hardness assumptions, we know that we can get BPL equals L. This is due to Cleavance and Van Malkebeek, and it follows the classical approach of hardness versus randomness. So here, what's the easiness that we need to assume? So we assume that there exists a function in D space O of n, so in linear space, instead of E in the time-bounded regime. Now we're talking about linear space. That requires circuits of exponential size. Then we can take any randomized algorithm that uses S space and simulate it deterministically in space O of S. And again, for roughly the same reasons, the hidden constant is large hidden constant. And the question we ask today is, can we de-randomize with small space overhead? Under assumptions, of course. So, questions till now? Okay. So, of course, we want kind of a recipe. We want to do it explicitly. We don't just want to ask for, what's C. We want to do it explicitly. We want to get C as small as possible. And, of course, we want to get plausible, nice hardness assumptions. Okay. So what do we get? So we show two sets of assumptions under which this constant C is almost 2. Okay, so BP space S is contained in D space 2 plus something small times S. And you should kind of think about it as paralleling the BP time T is contained in D time T squared. Okay, or almost T squared.
Can you say something about the number of tapes in this simulation?
Yeah, good question. So I'm assuming like I have like a constant number of work tapes, and this is a fixed constant, and that's it. Like I need at least, I don't know, 8 work tapes, and that's it. I'm fixing it.
You maintain 8 tapes?
Sorry?
In the other round, they also use 8 tapes?
Yes. And we also suggest an hypothesis under which this 2 becomes 1. So like the first set of assumptions is it's very plausible and standard. The second one is, we call it an hypothesis, and you'll soon see. Okay, but this is the state of affairs. And whenever I write here S, I mean a constant times log n for a large enough constant. Okay, so our results are constructive in the sense that if you give me a candidate hard function, and we'll also need a candidate cryptographic PRG, we show how to transform this a randomized algorithm into a deterministic one. And it follows from either PRGs or targeted PRGs. And also, we give a new evaluation method, which maybe I'll mention towards the end of my talk. And kind of as a technical component, we also give a new error correcting code, a local list decodable code, which, if you know, gives us a way to do hardness simplification. And here we do hardness simplification in TC0. So if you care about hardness simplification, and you don't need to know the randomization for it, the result we give is that if some language in linear space is hard for TC0 circuits of size 2 to the epsilon n, with oracle access to some function class f, then there exists L prime in linear space that's very hard for f. Okay, so this is hardness simplification where the overhead in the hardness simplification is a TC0 overhead. And this thing wasn't known before. Okay, the statement clear? Right, from a hardness to average case hardness. Yeah.
Just to rephrase it, so the encoder is a log space.
The encoder itself is log space. The decoder is also log space, but sorry.
Is it adaptive TC0 or non-adaptive TC0?
So it's non-adaptive. So it's adaptive TC0. If you want to do non-adaptive, we can also do not in TC0, but slightly larger. We can talk about it afterwards.
And it's like one or four reducible length error correlation, right? So it's in the
No, this is
error region.
right. Okay, good. So for our black box, so I said we have two sets of assumption. The first one is a black box result. The second one is a white box result. For our black box result, we construct PRGs. So, of of course, we don't need to define PRG. I mean, you see the definition, you know it. And PRGs are obviously very good for de-randomization because we can iterate over all seeds. And it turns out, and Salil mentioned it, that the correct model to fool, if you want to de-randomize space-bounded, is read once. I'm sorry, standard. Forgot to change it. So it's standard order. I did change it in the next slide because this is the correct model in which the machine reads its randomness, right? So each yi is like tossing a fresh random bit. Okay, so this is kind of the correct model to fool, and this is our PRGs fool those branching programs. Okay, so this is fairly standard. But first, we kind of reflect on the standard hardness to de-randomization result for BPL and ask whether it's really necessary to assume hardness against circuits like what Clevans and Van Meijkenbeek assume. And indeed it's not. So, I mean, stated differently, can the standard hardness to the randomness mechanism be performed with less overhead? And this is our result. This is kind of a preliminary warm-up result before the minimal overhead result. So assume we have a function in linear space that's hard for TC0 circuits of size 2 to the epsilon n with oracle access to those ROBPs, two ROBPs of length and width 2 to the epsilon n. Then we can take any randomized algorithm that uses S space and simulate it deterministically in space O of S. So this is kind of laying the groundwork and just getting like a better overhead. So this is still S to O of S, but this is kind of where we start. Okay, so we get a TC0 overhead in this framework. Okay, and it follows the classical design-based Nissan-Wigderson generator. Okay, so let's talk about our minimal footprint result. So the first one, the black box one, follows from worst-case non-uniform hardness assumptions and crypto assumptions. So what's the first assumption? For some constant big C, we have a function in D space C plus 1n, and the 1 can be, I don't know, 5, it doesn't really matter, that is hard for slightly smaller space, which is necessary, but given quite a few bits of advice, like 2 to the n over 2. Okay, this is the non-uniform hardness assumption. And the crypto assumption, I mean, I just want polystretch PRGs, which are very standard, but we also want it to be computable in log space. And we do give candidates for such PRGs. I won't get into it, but seems fairly standard. Okay, so if we have these two assumptions, we get this 2 plus little c, which little c is the universal constant, over the big C that comes from the assumption. So this hopefully is very small, so we get the 2 constant that I showed you. Okay, so how would I take this 2 and turn it into a 1? If this function f, the easiness thing that I want from it is to be computable in what's called catalytic space. So the catalytic model is a very cool notion in which you have little s amount of memory, which is like the standard working memory, but you have also capital S space of memory, which is not yours. You can use it, but then you need to store it to the original, to its original state. Now, usually, this is studied where big S is 2 to the little s. And it turns out it's very powerful. When little s is O of log n, catalytic space is TC1. But we wish to consider a more fine-grained separation. What do I mean by that? So remember that F was computable in C plus 1 times n space. So if most of this space was actually catalytic space, okay, so as you can see here, then we can get 1 plus little something times S. Okay, these are still PRGs. Okay, and I'll just mention, I probably won't have time to go over the construction. You can, of course, talk to me afterwards. But it goes along the Chantel 21 result with a new Hardin simplification and with a new method to space efficiently evaluate space-bounded machines over the PRG's image. And let's move on to the non-black box randomization results. And there we assume that we have a function computable in C plus 1 n space, but that cannot be compressible. So it cannot be efficiently compressible into a Turing machine that uses fewer space. Okay, this might be a mouthful, but know that it's a uniform hardness assumption, and it's a compression-based hardness assumption. So if you really want to know the hardness assumption, it's on that slide, but I don't want to go over everything. If you're really interested, I'll give you a few seconds to glance at it. But what I do want to emphasize is that you might think, well, we don't need to assume because we know that almost all strings do not have any concise representation. Right? This is from counting arguments. But the crux of the assumption is that we assume that such representations are also infeasible to find even for the outputs of F, which is easy in some sense because F is efficiently computable. Okay, this is why we need to assume and not just, yeah. Okay. So this is another set of assumptions under which we get C equals 2. Okay. Good. Now this does not follow from a PRG, but rather from a targeted PRG. And we've heard of targeted PRGs on Monday, and also about instance-wise randomization, right? In the sense that for a fixed X, if any attempt to compress fails, then the de-randomization succeeds on this particular X. Okay. How much time do I have after?
Maybe 3 minutes or so?
3 minutes or so.
4 minutes?
No, I'll do 3. Yeah. Yeah. You know what? Let me just tell you. Let's skip this. If you're interested in the code, then come talk to me after. I'll just mention that previously, if we wanted to get TC0 decoders, we could only get them up to certain hardness, which did not suffice for de-randomization. But we can now go all the way. And I'll just mention that the PRG is actually, it follows from the Chantel PRG. And it's it fits in one slide. It's a composition, basically, of the Nielsen-Wigderson generated, instantiated rather non-standardly, together with a cryptographic PRG, and a new way to evaluate, to kind of enumerate over all seeds. So if you, I'm sorry for skipping so many slides, but if you would kind of try to enumerate over all seeds of this PRG, and assuming Nielsen-Wigderson is very space efficient and the cryptographic PRG is very space efficient, you would get 3s plus O of log n. And we show that you don't even need a counter for the seeds. So we can even get rid of a dedicated counter to go over all seeds and get this 2s plus O of log n. Okay. I know it was fast, but if you're interested, then please come talk to me afterwards. So let's conclude with open problems. Some of it is work in progress. We don't like cryptographic PRGs in de-randomization and complexity works, usually. So it would be better to get rid of them and to assume only standard hardness assumptions. The second question is to weaken the uniform hardness assumption. What if we only allow the compression algorithm to be deterministic? This is a weakening one can consider. And a very interesting question, I think, is can we get both super fast and minimal memory waste simultaneously? So the same algorithm would also would incur both very small overhead in time and very small overhead in space. Okay. Yeah. So thanks.
As for your assumption involving catalytic composition, do you have any candidates for the hardness?
Yeah, that's a good question. No, that's why we kind of said it's a hypothesis. So just put more of like putting forward studying catalytic, not in the S2 to the S separation, but in the more fine-grained setting.
Can you say something about why you get upper bounding catalytic composition?
Why we get what?
Why you
The 1 plus?
Why catalytic composition occurs here?
Because when we ask, so in the de-randomization, in evaluating the PRG, we repeatedly ask for the computation of F on like smaller inputs, right? So if we could reuse the space, we can kind of compute F and then use the same space to kind of, return the control to the other algorithms, like to the G crypt or M, and they can just reuse the space. So it's like, maybe I can show you after.
Yeah.
Okay.
So in the time case, I thought there was some evidence that you need to pay at least a square or a
That's right.
rent.
That's right.
But I didn't see it when you talked about getting the constant down to 1 in your. So is there an additive log n, or is it not necessary to have that same analogous kind of loss?
Well, the additive, so we will have additive log n, but like plus 5 log n. But I mean, we consider S's which are omega log n for some large enough. Yeah, but I don't think. So can you repeat the question? Maybe I just.
So it's like 1 plus epsilon times S plus.
Wait, sorry. 1 plus epsilon.
Times S, the space of the randomized algorithm,
Right.
plus some 5.
Right. Yeah. Exactly.
And is there evidence also there that that's kind of like something like that is the best one can hope for in the space?
No, we don't know. We don't know how to kind of scale the impossibility results in the time bounded to the space setting.
So let's thank Lee again.